So the topic for the Cosmology crew, we'll talk about the CMB and the power spectrum. In the CMB, there's density fluctuation, delta, about the background field, and because this is randomly distributed, so the mean values of the distance fluctuation delta is just 0. The two correlation functions of the delta is non-zero, and due to the homogeneity and isotropic is only dependent to the radial part. And if we plot the 2-point correlation functions over the distance, then this makes a bump, which is coming from the Bayer-Nokosi relation PAL. And by the Fourier transformations, we can obtain the power spectrum in the K space. So here's some step by step for the Fourier transformations and delta function. So the results, the power spectrum becomes the Fourier transformations of the 2-point correlation functions. So here's the definitions of the power spectrum PK, 2-point correlation functions for the K mode density fluctuations, and this is moment conservation, and the PK is the power spectrum. So if we plot the power spectrums over each K mode, in the large scale and the low K, the power spectrum PK is proportional to the K to the NS. NS is called the tilt and spectral index. And in the high K and the small scale, power spectrums that decrease over the K is proportional to the K to the NS minus 4. And there's some fluctuated behavior which comes from the Bayer-Nokosi relation. And such fluctuation behavior makes a bump in the 2-point correlation function plot. This can be obtained by the convolution between the Gaussian functions in the real space. And if we calculate the Fourier transformation of this, then this becomes a sign, and the convolution to the Gaussian functions. Such analysis is called the tilt or spectral index, and this comes from the quantum perturbation of the impulsion. And we know that the value of the analysis is around 0.96 from the Planck measurement. So here, so the density fluctuation measures, and the power spectrum is the proportional to the square of the delta K. And we can define the dimensionless power spectrum. Let's consider some sphere with specific radius, and the dimensionless power spectrum that defines as K cube times the PK of the 2 pi scale. This is called the delta scale K, or the curly K. And if we calculate the convolutions of the spheres and the dimensionless power spectrum, we can obtain the sigma R. So why the dimensionless is given like the letter we talked about it yesterday. The delta functions has volumes V from the Fourier transform relations, and the density fluctuation has was mentioned with the 0, but by the Fourier transformations, the density fluctuation in the K mode has the dimension of the V. So the power spectrum of the dimension of the V, so the K cube times the PK become the dimensionless quantity. And if we plus the density fluctuations at a specific radius R, then probability distributions are given like the Gaussian form. And for the 8 megaparsecs, some of the galaxy scale, we can measure the variance of this probability distribution, which is equal to sigma 8. This implies that how much the difference between the dense and the not dense regions. And there's S8 tension. We can measure the combination of the sigma 8 and the matter parameters. And so the S8 tensions mean that the CMB observation and the presence observations are not consistent. So such S8 tensions are related with the fluctuations in amplitude. the variance of the density fluctuation. There are also similar tensions, trouble tension, which is problems in the distance. So the dimensionless power spectrum show that such a behavior. And if we convolution through with Bessel function, this comes in from the Fourier transformation of this pure step function, then this yield the sigma r. The Baranov-Cauchy oscillation gears coming from the density fluctuations and some specific sound horizon. This makes some specific distance, and separation of the star or galaxy, such as structures groups. The collapse object has some such a sound horizon distance separation. This makes the bump in the two-point correlation function. Now I will turn to the matter power spectrum PMK. This is originally generated from the primordial power spectrum, which comes from the impulsion. The R means that the curvature perturbation, which is the gauge invariant quantity. Usually the R contains the impulsion's color field, but so we can define the zetas, which comes from the density fluctuation. Also, this is the gauge invariant quantity. And by multiplication of the transfer function, this includes the evolutions of the universe, allowing the radiation dominant and matter dominant, so the BBN informations are included in that, and the additional factors are multiplied. So by multiplied transfer functions on the primordial power spectrum from the impulsion, we can obtain the power spectrum through which it can be observed. So in latest, we'll talk about the why the power spectrum show that such a behaviors for each K mode from by considering the K dependence of transfer functions that are the primordial power spectrum. So also there is a linear growth factor, but I will not discuss in detail. And such a power spectrum that becomes shift linearly, but such a linear shift region becomes narrow. So when the jet lag shift becomes small in the present time, there's a nonlinear evolution for the small scale, which means the high K. So this formula, the convolution with the transfer function and the primordial power spectrum, is only valid for such a linear regions. We can plot the co-moving horizon here. 1 over AH. This comes from the horizon distance. Light moves during the Hubble time, and we set the C equal to the 1. And such a co-moving horizon can be plotted like that, with each approach impulsions, radiation dominance, matter dominance, and dark energy dominant. We can calculate the co-moving distance, co-moving horizon, from the first Rademacher equation. This is first one. In the radiation dominant, the low is proportional to the minus 40, so the R1 over H is proportional to the A. And for the matter domination, A to the 1/2. But the radiations in the matter dominations, the horizons are increases over the time, but in the dark energy dominant in the late universe, because the energy density is constant, the 1 over H is proportional to the 1/2, so the horizons are decreasing. So the co-moving horizons, such as 1 over AH, which means that the maximum distance communicating during the Hubble times is an increase for the standard cases, but in the accelerated expansion, such a horizons are decreased. So if we consider some specific scale, for example, the 10 gigaparsec, then there are no communications for such a scale. The horizon side, this is horizon side, this graph is horizon side. But if we consider gigaparsec scale, then at this approach, in this approach, the horizon, this scale was inside of the horizon, but so the gigaparsec is still outside the horizon during the radiation dominant. So at the radiation dominant, the CMB commutes the information by the causality, but this scale is outside of the horizon, so that it induces the horizon problem. So this requires that the additional accelerated expansion are put in the early universe, so that this requires impulsions in the extreme of the universe, so that the horizon becomes decreased in this time, so that the such a specific scale, for example, the gigaparsecs, becomes inside the horizon. This is the horizon. So CMB is, can be consistent with the observational results. So impulations makes such a same information for each patches by decreasing the horizon of the time. So here, this is the impulsion approach. There are some specific scale, and at this approach, the scales are inside of the horizon. So in such a horizons, the scalar curvature perturbation evolves, so that this becomes a causal. But in outside of the horizon, such as scalar curvature perturbation R and the zeta, so it's coming from the density fluctuation becomes a constant for the outside horizon. There's no evolutions of it. Again, the inside of the horizon, for the matter dominations, the scale becomes such as some specific scales. R is in the horizon source. This makes the evolutions of the some density fluctuations or the scalar perturbation, which makes the these effects can expressed by the transfer function, and eventually this makes the large scale structures in the universe. There are some specific relation between the gravitational potentials satisfied such a force equation at the specific gauges, and the relation between the gravitational potential pi and the zeta is given like that. This is one solution. So if we insert the equation of the state for the radiation dominance and the matter dominance, and the relation between the radiation's dominance gravitational waves and gravitational potential, and the matter dominant MD's gravitational potential, and these two ones are constants. And when the universe turns to the altitude MD, there is additional factors that appears between the gravitational potential capital pi. And such a gravitational potential capital pi is the constants for the super horizon, so we can calculate how the matter's fluctuations evolves over the time. So we know that this is the Poisson equation, and there's a case in here. Delta M represents the matter perturbations, and the lows evolves at the 8 to the minus 4 to the RD and 8 to the minus 3 to the MD. So for the delta M, that is proportional to the case, and delta M is proportional A. This is case of the super horizon when the gravitational potential becomes constant. So we can also calculate sub-horizon cases. This requires that solving the equation of motion for the density fluctuation. So that here is the result. How the matter's perturbation delta arms evolve for each approach radiation dominant and the matter dominant era. And for the super horizon case, the delta arms are proportional to the A case, delta arms are proportional to the A for the matter dominant case. But sub horizon case, the matter fluctuation delta arms is evolved as a logarithm of A, even though this is very small. But if the dark matter is below this one, then this can ensure that the structures of the universe can generate this. And but the baryon case, in the baryon case, the baryons and the photons are coupling with each other, so the baryon cannot borrow such evolution, so the baryon cannot make the such a large scale structure. We will talk about latest one more time. This is the very important one. So now let's compare the two different scale. One is a gigaparsec and the other one is a megaparsec. During the radiation dominant, both scales is outside of the horizon. This thick line is the horizon side. So this is outside the horizon, so the delta M is a proportional to the A scale. But there's such a small scale can stay more in the sub-horizon here. Small scale can get inside in the sub-horizon. So the in the small scale case, because this is staying more in the sub-horizon during the radiation, this makes the additional evolutions with the logarithm compared to with the large scale. One more time, the small scale stays there more in the sub-horizon during the radiation, so with evolutions of the logarithm, this makes the relatively large evolution. So we can parameterize the parameter power spectrum from the impulations with the amplitude AS and the spectral index NS to the K. That pivot numbers can be set by some specific value, and AS is order of 10 to the minus 9 and NS is 0.96, and that pivot value is the radiation random matter equality, so that the critical values when some specific scale, the Kp, across such a radiation and the matter dominant equality, so that at that specific critical scale, above the scale, above the scale, it cannot get into the Sach-Wolfson, but below the scale, that values can stay in the Sach-Wolfson during the radiation dominant. So this pivot, the critical value Kp at the radiation and the matter equalities correspond the corresponding values of the inverse of the horizon size. This makes the different behaviors around that value. So in the high K, in the small scale mean that there's evolutions with the logarithm. So this makes a subtraction. So the transfer function can be written as a subtraction in the small scale to the k to the minus 2. In later, I will derive the exact proportionality of the power spectrums about the K mode. So we can obtain the relation between the primordial one and the present one from the such a cosmic equation, the some of the derivation and the relation of it. And now here is some of the K dependence of the power spectrum. Here, the dimensionless power spectrum delta is given like such a form. So here this is transfer function. Below that the Kp, this is K0. Above the Kp, the pivot K, transfer function is the k to the minus 2, and there's a k to the both factors, and that power spectrum has the k to the ns minus 1 and the k cubic factors here. So if we insert each cases for the low k, the transfer function is k0, so this is the k to the ns, and for the high k, transfer function is k to the minus 2, so k minus 4, this is the k to the ns minus 4. So this makes the power spectrum. So in the small scale, this can insert to the horizon side more during the radiation dominance. This makes the Laplacian behavior. Now, in the remaining time, I will talk about the density perturbations briefly. From the fluid mechanics, there are two conservation equations. From the another conservation, there is a continuity equation, and then from the momentum conservation, there is Euler equation, and the gravitational potential satisfied by the first equation. Without the expansions, we can expand this with the burst order. For the density, we can define the deltas. For the flashes, we can define the sound of the speed. And as a result, the equation of the motions are given like that, how many would you like to form. And the frequencies can be the negatives or positives depending on the comparison between the gravitational and the Project factor. And if the gravity factor becomes larger than the Genesis instabilities that appears, this is a classical result. And if we insert the expansion, then there is a damping term from the Hubble frictions, and the gradient includes a scale factor. So first of all, we can calculate the also this yield that user of Friedmann equations result, and for the first order perturbation radial, we show that the equation of motion includes the damping term and expansion one. But such a classical result without the general relativity is only valid for the matrix and the sub-horizon cases. But for the radiations and the super-horizon cases, it requires that the general relativity is with the gravity impact. But let's only focus on the sub-horizon cases and the delta M. By inserting the Hubble density as a function of the time in the equation of the motions, and the CS is equal to the juice for the matter perturbation, then the solution becomes the logarithm of the I. Already we discussed that. In the sub-horizon, the radiation dominant matters perturbation follows the logarithm A. But for the baryon case, the baryons are coupled to the photons, so that it cannot go like such a behavior. But the dark matter is test such a density fluctuation still grows at the radiation dominant, which eventually is make the structure. But for the radiation one, the Jeans length is corresponding to model H is the sort of sub-horizon case. The radiation cannot grow at the such a radiation dominant approach. Final one, I want to talk about the ISW integrates Sach-Wolfson impact as a dynamical measurement. Not only the density perturbation, we can also consider the evolution of the gravitational potential capital pi with the specific equation of the motion. In the meta-dominant case, the capital pi gravitational potential is constant, but the dark energy dominance in the late-time universe with the low redshift jet, such a gravitational potential capital pi is the decrease over the time. So that this makes the when the CMB light past the cluster, there's a gravitational potential around the cluster. It lost the energy, and it gained the energy, and it lost the energy. But the gravitation, it gained energy when the CMB lights get into the cluster, and it lost energy when the CMB lights get out from this cluster. But in the dark energy dominant cases, the energy gain is larger than energy loss because the gravitational constants decrease over the time. So when the CMB lights pass through the cluster, the temperature and the isotropy from the CMB increases. But when the CMB lights pass over the voids, such temperature and isotropy becomes decreased. So this is called integrates the Sach-Wolfson impact, so-called ISW, and the evidence of the dark energy. By measuring the large scale structures in the low jet, we can track the dark energy. This is one example of the dynamical measurement. So in these videos also we talk about many things. We define the two-point correlation functions and the power spectrums and the dimensionless one. Such a power spectrum contains many information, especially in the K modes. This kind of sign the transfer functions and the primordial power spectrums and the K dependency can check. And also the density fluctuation, especially the matter ones, evolves over the scale factor. So in the case of the radiation and the matter dominance approach, depending on each K mode of the super and the sub-horizon. So this is the power spectrum, and then maybe the remaining one is the linear perturbation of the part 1 for this Cosmology school.